Okay, hello everyone. Thank you for joining us this time. So this is our third colloquium this fall. And today we're going to discuss how electrochemistry can drive molecular catalysis. As you know, heterogeneous electrocatalysis is not the only way to activate small molecules, for example, oxygen or hydrogen. And there is another way, which is to use intermediate molecules. And those intermediate molecules can first be activated electrochemically and then can drive the transformations of target molecules in the solution. So those intermediate molecules can be either redox mediators, meaning that they can just pass charge and essentially acting as a charge shuttles, or chemical catalysts. And those chemical catalysts, of course, have to be activated electrochemically prior to the reaction. So that basically means that we should have a big bridge between the electrochemistry and chemical catalysis. And obviously such a bridge exists, and that represents an entire research field. So in today's colloquium, we're hosting Professor Cyrille Costentin, who is widely recognized in the community as an expert in molecular catalysis, homogeneous electrocatalysis, and the proton-coupled electron transfer reactions. So we will have today a very good opportunity to discuss the molecular catalysis field, and especially from the electrochemistry point of view, and learn about the developments in this field, of course. Cyrille received his PhD at the University of Paris in 2000 in the group of Professor Jean-Michel Sévian. And later he was a postdoc at the University of Rochester. And then he moved back to University of Paris and became a professor there. And since 2019, he's also a professor at the University of Grenoble-Alpes. So Cyrille, thank you so much for the opportunity to host your colloquium. And now, of course, the stage is yours.
Thank you very much, Andrew. First of all, thank you for the invitation, and thank you for all of you attending this presentation. So, as mentioned by Andrew, I will discuss today molecular catalysis of electrochemical reactions, and I will start by describing the principles of doing molecular catalysis for electrochemical reactions, and then in the second part I will try to show you some applications to small molecule activations. So, okay, yeah. So I guess that there is no need to convince you that we have to electrify the world, and especially we have to electrify chemistry. And a way to do that is to use electricity that you can get from renewable source, for example, light, and then use electrochemistry to convert small molecules to make fuels, and then you can use these fuels to make reactions. But you can also generate reactants such as chlorine, for example, and use them to make products. So there is, for example, an example in this recent science paper. So then this means that in the middle here we have electrochemistry, and as you know, running an electrolysis is a puzzle in the sense that you have to make working together different pieces, which means that you have to run a cathodic reaction at the same time as an anodic reactions, and in between usually you need a membrane, and you need to design a cell and manage ions flux across the membrane, and you have also to manage how you get the substrate and how you recover the products. So it's kind of complicated. And so today I will just focus on one piece of the puzzle, which is the cathodic reaction. But even if you're interested just in the cathodic reaction, you have to keep in mind that you have several points to optimize, which is the rate of the reaction, so the current, which will depend on the energy input, actually the potential you apply at the electrode. And you have to worry about how you get the substrate to the electrode, how you recover the product. And of course, you may have a selectivity issue if you have different products. And so in most of the cases, you have to do catalysis to get only one product at an efficient rate and with low energy input. So we end up with the idea that we have to focus on electrocatalysis. And as mentioned by Andrew in his introduction, there are different kinds of electrocatalysis. And if we talk about electrocatalysis, we have to discuss in more details about what we are talking about. And so we have to describe the crime scene, I would say, which means what's going on close to the electrode surface. So one possibility is that the reaction takes place exactly at the surface of the electrode material. In that case, I would call that electrocatalysis, okay? But you can also have reaction in the double layer or in the bulk of the reaction. And what I'm gonna discuss today is molecular catalysis, where we have homogeneous catalyst in the bulk of the reaction. And this is where the catalysis will take place. And the electrode will just be here for the catalyst to pick up electron and diffuse back and forth between the electrode and the solution where the catalysis takes place. The reason why we are doing this is because we are trying to focus on the actual activity of the catalyst to reduce a substrate or oxidize a substrate. Okay, and so we do not want to have influence of the double layer here. But I will try, maybe at the end of the talk I will discuss a little bit about what's going on if catalysis take place in the double layer. Okay, so after this short introduction, let's go into the details about molecular catalysis of electrochemical reaction, and I should say homogeneous molecular catalysis of electrochemical reactions. Let's describe first the methodology that we have to use. Usually, so you put the catalyst into the solution and you run an electrolysis, and using analytical technique, you analyze the product so that you can get information on selectivity and durability by looking at the current over time. But then if you want to investigate the mechanism in more details, you need an analytical method such as cyclic voltammetry or rotating disk voltammetry. I will today focus on cyclic voltammetry. It's very useful because you can have a fast response, and importantly, you have a control of the hydrodynamics in the solution with the scan rate or the rotation of the electrode in RDV, for example. So what's the basic principle if you use cyclic voltammetry, for example? So let's consider the reduction of a substrate A that you can do directly at the electrode. Usually this direct reduction, if the electrode is not a catalytic electrode, you would get a very negative potential, for example, to get the direct reduction of the product. Okay, so the idea is now to reduce the overpotential by using a molecule that you design to be able to reduce your substrate in solution. And then you can have two different kinds of situations. First, what we can call redox catalysis is when the catalyst that you use picks up an electron at the electrode and then is just there to transfer one electron, usually in an outer sphere manner, to the substrate, okay, to regenerate the catalyst, okay? And this is redox catalysis in a sense that there is no special interaction between the homogeneous catalyst and the substrate. What is more interesting is the case of chemical catalysis, where you design the catalyst so that you will get a chemical interaction between the reduced form of the catalyst and the substrate. And this is where you can get very efficient catalysis because you will lower the energy that you need to activate the substrate this way. And so what do you observe in cyclic voltammetry? In absence of substrate, the catalyst PQ gives you a reversible wave, and then in the presence of the substrate, you observe an enhancement of the current because you regenerate the catalyst, okay? And then what you observe in such a situation is that the overpotential you will get is directly related to the standard potential of the PQ catalyst that you choose, okay? So now, to understand where we have to focus on our attention to understand what's going on in the solution, let's take a look at the concentration profile at large overpotential during a CEV. In absence of substrate, you have the classical CEV for reversible copper, and at high potential, negative in the case of a reduction, you have transformed into the reduced form of the catalyst, or the catalyst that is close to the electrode surface. And then you have a concentration profile in the diffusion layer, which size depends on the scan rate. Now, in the presence of the substrate, as you can see here, at high overpotential, when you're on the plateau here, I will discuss later on this plateau, you can see that now the concentration profile is squeezed in a very thin reaction layer close to the electrode surface. It is due to the fact that while the reduced form of the catalyst is diffusing away from the electrode, it reacts with the substrate and gives you back the oxidized form again. And so this reduces the size of the solution where you have a reaction. And so basically, the reaction takes place only in this reaction diffusion layer, which size is roughly given by the square root of the diffusion coefficient of the catalyst divided by the rate constant of the reduction of your substrate with the molecular catalyst. Okay, so now that we have... Yes.
I'm sorry, can I just very quickly ask you to clarify the term substrate, because just so that everyone is on the same foot, because it's not quite in the traditional way. Yeah.
So what I call a substrate is the molecule you would like to transform. For example, in the example I will discuss later on, this can be CO2, or this can be an acid to make hydrogen. It's not the electrode surface. Okay. So now let's take a simple example for one electron, one step mechanism. You have the catalyst PQ. You reduce the catalyst, and then the reduced form of the catalyst react with your substrate A to give the product B, and recover the catalyst, and so then this can turn over. So here's the picture. At the electrode surface, you just have an electron transfer to generate your reductant, okay? This occurs in the diffusion layer, and this is governed by the Nernst law. And now you have this diffusion reaction layer that I was describing previously, and the efficiency of the catalysis depends on the dimensionless parameter, which is the ratio of this pseudo first order reaction rate constant, okay, the bimolecular rate constant times the concentration of the substrate, divided by the time scale of the CV, which is FV over RT, okay? And then you have a second parameter that controls the CV response that depends on how much of the substrate you will consume during the CV. And so it depends on this dimensionless parameter as well that involve the rate constant of the catalytic process, the time scale of the CV, and of course the ratio between the amount of substrate you have in solution and the amount of catalyst you have put in solution as well. If you have an excess of substrate, of course, during the CV, you won't consume a lot of substrate, and so the diffusion of the substrate will not be important. So if the system is controlled by two dimensionless parameters, we can draw a zone diagram describing the different situation that we can have. Okay, here is the zone diagram. If you have either a small amount of substrate or a very low rate constant, you have no catalysis. You just see the CV of the catalyst. Now, in the opposite situation, at high concentration of substrate and high rate constant, you're in this zone here where you end up with an S-shaped steady state CV with a plateau. And this is very interesting because the plateau current is now directly proportional to the square root of the rate constant. So you can very easily extract the kinetic information on the catalytic process from the plateau current. And of course, experimentally, you're not always in that situation, but as you can see, you can play around with the scan rate or the concentration of the substrate. If you increase the scan rate, for example, you will move the system down and you may get a chance to reach the zone where you observe the plateau. Or if you're in this situation, you can increase the concentration of the substrate to move the system toward this interesting zone where it's easy to get the rate constant. So let me just show you very quickly a real example. Here is the situation of a system that I will describe in more details later on. The reduction of CO2 using iron TTP porphyrin as a catalyst in the presence of high concentration of proton donor. At low scan rate, you get a peak CV here because you consume because you get inhibition of the electrode. Now, because you produce CO that is an inhibitor of the electrode surface. Now, if you increase the scan rate, of course, you decrease the time scale of the CV, and so the charge that you pass is smaller. And so you can reach this plateau now, which is the ideal situation. And you can see that at two different scan rates, you get more or less the same current, which means that you have reached a steady state where you can get the kinetic information from the plateau here. There is another interesting situation. If I go back to the zone diagram, which is the total catalysis situation, where the catalysis is so fast that or the concentration of the substrate is so small that you will consume all the substrate close to in the diffusion reaction layer, and you will get a peak-shaped CV because the CV will be controlled by diffusion of the substrate. And in that case, as you can see, there is no more information from the plateau, from the current here, because the current here is controlled by diffusion of the substrate. So the current peak is just proportional to the concentration of the substrate and the diffusion coefficient of the substrate, or the square root of the diffusion coefficient of the square root of the substrate, sorry. But now you can get an information from the position of the peak. As you can see from the expression of the peak potential, it depends on the rate constant. And as you can see from this experimental example, a different concentration of acid here, but this is not important. You can see that you have a peak, a catalytic peak here, which potential change with the concentration of the substrate, which is here, and from the slope here, which is 30 millivolt, you can conclude that you are in the total catalysis regime. And so from the position of the wave, knowing the standard potential of the catalyst, you can extract the rate constant. So as you can see, there are many different ways to extract the rate constant from the CV. Okay. Of course, you may be in a situation where neither the plateau current nor the total catalysis can be reached. but in that case, you have to rely on simulation to extract the kinetic information. If you do not get a plateau, then if you know the excess factor, which is the ratio of the concentration of the substrate divided by the concentration of the catalyst, then one of the governing parameter is fixed, and then the CV only depends, or the current that you measure in CV only depends on one dimensionless parameter. So by simulation, you can predict the current of the catalytic CV as function of this parameter for a given excess factor. And then you measure experimentally the increase of the current, and you use this value of the increase of the current in the presence of the substrate. And from the position of this experimental data point, on the working curve, then you can get the dimensionless parameter. Okay, knowing the scan rate, you can measure the rate constant. Okay, so this is how you have to treat the experimental data to extract kinetic information and to get the rate constant for a given catalyst in given conditions. Now, let's say you are interested in a specific reaction and you would like to compare different molecular catalysts. Of course, you have different benchmarking parameter. One is the selectivity. If you compare different catalysts, you have to know whether each catalyst gives the same selectivity if you're looking at a reaction that gives different products. Another parameter that I will discuss later on is the intrinsic activity, the turnover frequency, that, as you can expect, depends on the rate constant for the reduction of your substrate by the electrogenerate catalyst. Then there is a third parameter which is important, which is the durability of the catalyst that you can characterize by the maximal or limited turnover number.
I guess we have a loss of connection, so let's wait just for another minute. Hopefully, Cyrille will connect back.
I'm sorry. Do you hear me?
Yes, welcome back.
I'm very sorry. I lost the connection for whatever reason.
No problem.
Okay. I'm sorry. Okay, so I was saying that one important parameter is the durability that correspond to the maximal turnover number that you can get, and this durability can be obtained simply by running a long-term electrolysis until the current is zero. Okay, but you can also get this turnover number from short-term electrolysis and extrapolate the deviation that you observe from linearity of the increase of the turnover number with time. What I would like to emphasize here is that this turnover number depends on the characteristic of the cell, okay? I should say that the way the turnover number change over time depends on the characteristic of the cell, because as you can see here, it depends on the ratio of the surface area of the electrode and the volume of the cathodic compartment if you're running on reduction, for example. Now I will focus on the intrinsic activity. The intrinsic activity of the catalyst is the turnover frequency, and so it is related to what's going on in the diffusion reaction layer in a situation where there is no degradation of the catalyst. And of course, you can relate the amount of product that you accumulate in a solution to the efficiency of the reaction in the diffusion reaction layer. So what matters is the number of catalysts that you have in this diffusion reaction layer. So you have to define the turnover frequency as the ratio of the number of molecules that you create per unit of time divided by the number of molecules that you have in the diffusion reaction layer. Okay? And it's not simply the current that gives you this information, because again, as you can see from the expression of the current also depends on the cell geometry. And of course, if you want something that is intrinsic to your catalyst, you have to remove this dependence of the current on this cell geometry parameter. And this is obtained if you actually divided the current that gives you the number of molecules you produce per unit of time, divided by the number of molecules in the diffusion reaction layer. As you can see here, if you define the turnover number and then the turnover frequency this way, you obtain an expression of the turnover frequency that is independent on the cell geometry and is only specific on the characteristic of your catalyst, which means its standard potential that will control the over potential, and the catalytic rate, which will give you the efficiency of the reaction, the homogeneous reaction. And of course, you have to be careful, because if you define the turnover frequency without taking into account only the catalyst in the diffusion reaction layer, as I just mentioned, your turnover frequency will depend on the cell geometry and will not be characteristic of the catalyst. Okay? So now let's introduce some more complexity. So far, I have assumed that the electron transfer between the catalyst and the electrode surface is efficient and just governed by the Nernst equation. Of course, it's not always the case, and sometimes you have some sluggishness for the electron transfer between the electrode and the catalyst. And in that case, as you can see from this schematic CV here, instead of having the S-shaped CV, which is governed, which shape is governed by the Nernst equation, you have something which is more sluggish here. And the problem is that in that region here, the current is no more controlled by the catalytic reaction. As you can see here, the current will be controlled by the rate constant for electron transfer between the catalyst and the electrode. Okay? And so in such a case, the only way to get rid of this problem is to reach the plateau current, where you get an overpotential which is large enough so that there is no more influence of the electron transfer kinetic between the catalyst and the electrode. Okay, then you can recover a kinetic information from the catalyst, from the plateau. It's also true at very small overpotential, as you can see here or here. But in that case, you have a very small current, and so it's very difficult to extract kinetic information. So I would recommend in all the specific case, if you would like to extract the kinetic information, is to try to reach the situation where you observe a plateau, and sometimes, of course, experimentally it's difficult to observe this plateau. But if you reach a CV where the current becomes independent or very little, or if you observe very little dependence on the scan rate, this is a good information that you probably have reached the plateau, and you can extract the kinetic information on your catalyst. Okay, so just to finish this, you may say, okay, I have only presented so far a very simple system where you have just one electron transfer and one chemical step between the substrate and the catalyst. Whereas typical reactions involve more than one electron. Here are some examples. If you reduce the proton to make hydrogen, if you reduce CO2 to make CO or formic acid, or if you reduce oxygen to make H2O2, or even more, if you reduce oxygen to make water, you will need a 2 electron or 4 electron process. And so the question might be, how does it affect the preceding methodology? Which kind of kinetic information will you get if you have several steps, if you obtain a plateau CV, for example? Well, actually, this is not a simple situation, because you have to consider the different 2 electron, 2-step possible processes. And here I won't go through the details, but you can have first electron transfer, then a second electron transfer, and then you generate your active form of the catalyst, and it's followed by reaction with the substrate, makes an intermediate, and then react with the co-substrate, for example, an acid, to get the final product and regenerate the catalyst. Or you can have electron transfer, then chemical step, then second electron transfer. But this second electron transfer can be easier or more difficult than the first one, and so on and so on. So it's not an easy problem, but the different situations have been described in the literature. Of course, I don't have time to go through all the details, but I will just give you one example. If you consider, for example, the EC process, which means first an electron transfer, then a reaction with a substrate to make an intermediate that is further reduced, and react with the co-substrate to get the product and regenerate the catalyst, you have 2 chemical steps, okay? If you assume that the second electron transfer is easier than the first one, okay, you will observe just one wave, okay? And so you need 2 kinetic information to characterize the 2 chemical steps. And actually, you can get 2 kinetic information, because on the CV, let's assume that you have an excess of substrate so that you reach a plateau. You have on this S-shaped CV 2 kinetic information. One is the plateau current, the one that we have used previously, but you have also another kinetic information, which is the half-wave potential, which is, in other words, the position of the wave. And as you can see from the analytical expression of the plateau current and the half-wave potential, they both depend on the 2 chemical steps here. And so by a combination of the position of the wave and the plateau current, you can actually extract the 2 rate constant here. And of course, if you have a substrate and a co-substrate, you can play around a little bit with the concentrations to push the system in a situation where one is rate determining or the other one is rate determining. So to make the situation clear, we have the tools to analyze 2 electron, 2-step processes Okay, and so now the next step will be to show you some examples of how we can extract those information from real system and use, which is the goal, use those information to improve the molecular catalyst for a given reaction. And so I suggest to you to make a short break now and to continue the second part in 5 minutes, where I will show you experimental examples. Thank you. So if you have questions on the first part, I guess that it's time to ask. And sorry again for the problem I had in the middle of the presentation.
Thank you, Cyrille. Any questions that the audience has? So you can ask questions directly. Maybe I can start then. What I was wondering if you can maybe give us some idea of the limitations of this approach. So, for example, do you have to care about the size of the molecule that is used as a catalyst? If it becomes really big or not? And of course, the concentration ranges, like all these things that you have to know.
So yeah, I will show you examples later on, but typically the concentration you can use is millimolar for the catalyst. Okay, this is the typical 1 millimolar, or maybe smaller, but because you have to be able to observe the wave of the catalyst in absence of substrate, so that you get the standard potential. Okay, but one difficulty is sometimes to get the situation where you have an excess of product, because to reach the plateau you need to be in a situation where the excess of substrate is large enough. Okay, and so you have to play around with the ratio between the substrate and the catalyst. Okay, so sometimes you have to decrease the concentration of the catalyst to reach a high enough ratio, like a factor of 10, for example, at least, to be able to reach this situation. As I mentioned also, one way to reach the plateau current to extract easily the rate constant is to increase the scan rate. And as you may know, increasing the scan rate introduce some more difficulties, because the capacitive current will increase. Okay, so that might be a problem sometimes. So you can, if you have a, I would say, if you are running if you have a catalyst which is in a range of potential where your electrode surface is, I would say, clean or innocent in terms of capacitive current, okay, then you can reach scan rate as high as, let's say, 20 volts per second or 50 volts per second to observe the catalytic current, and that's fine. Okay. Of course, another limitation is that you need to have a catalyst which is efficient enough, because if you increase the scan rate, of course, you decrease the competition between the time scale of your CV and the catalytic process. And so if the scan rate is too high and your catalytic process too slow, okay, you will not see catalysis. But I would say that if your catalyst is not efficient enough, this means that it is not worth trying to get kinetic information. So typically you need a catalyst which has a rate constant, in a bimolecular rate constant in the range of, I would say, 10 to the 5 per mole per second, something like that, to be able to observe a decent current and analyze the catalysis.
Okay. And I'm wondering also regarding the capacitance. So if to eliminate the capacitive current, would you say that it's possible to use, say, pulse voltammetry and somehow just redo the math to get fewer information?
Yes, in principle, it's possible. Yeah. Yes, it is possible. Yeah, it's possible. I've seen that there is a question in chat asking about the software that can be used to extract information. Yes, of course. You can use like commercial software such as DGSIM or DGH or KISA, which are software that you can use to simulate the CVs. And so what I would recommend is that usually this is the way, I think this is the best practice would be to once you have a catalytic current, first it's first important to run, if you use CV, for example, to run CVs in different situations, different scan rate, different concentration, and so on. And from that, to try to get an idea of what's going on and to get an idea of which kind of situation you have. Okay, as you'll see in a minute, when whether the position of the wave is similar to the standard potential of the catalyst or not, and so on. And from that, you can get a first idea of what is the rate limiting step of your process. And then from that, you can extract kinetic information from analytical expression. And once you have those values, then you can go to simulations to see if by using simulations, you recover something that makes sense with what you have experimentally. And then, so another way to say it is to use the analytical expression to obtain guess value for the rate constant that you have to put in the in the software to run simulations. Okay.
Yeah, there is another question from Julia. I mean, you can try to unmute yourself, or probably would be better if you can ask directly.
Okay. So.
Oh, okay. So the question is.
Okay, the similarity with electrocatalysis. Well, I would say that it's possible. I mean, there are some similarities, and to move from molecular catalysis to electrocatalysis, I would say that you have to go step by step. And this is something I will try to discuss a little bit at the end of the second part, which is first, I have discussed here only homogeneous catalysis, okay, with the catalyst in solution. Then you can do the same kind of analysis by considering the catalyst attached onto the electrode. So no diffusion. And actually it's the math is simpler, okay? And then you can say, okay, what's going on if now the catalyst is no more just a molecule attached onto the electrode, but now it is part of the electrode surface, okay? And then the situation becomes a little bit different. And so I would say that you can, in principle, make a distinction between molecular catalysis and electrocatalysis. And so even though the CVs may look the same, okay, I think that the way you have to envision the catalytic process is not exactly the same. And this is something I will try to mention at the end of the talk. So I will go back to this.
Yeah, I think that also answers the questions that were asked in the YouTube chat. So maybe at this point, Cyrille, we can continue.
Okay.
Thank you.
Okay. Sure, thank you. So let me go back. Okay, so now I will continue our journey on molecular catalysis of electrochemical reaction, showing you some application to small molecule activations. So I will start with a very classical, I would say, example, which is the analysis of the reduction of CO2 to CO using iron porphyrins. Iron porphyrins are very useful in that way because they are very robust catalysts, and so we have been able to get a lot of information. And so I think it's a good example to show you how you can use the CV to analyze the mechanism and maybe improve the catalytic process. So here is an example of the CV that you can get in organic solvent. Okay, the reason why we use organic solvents is because the solubility of CO2 is very large. So in blue here you have the CV of iron porphyrins, where you have two successive waves. If you start with iron 2 porphyrins, you can reduce it twice, and you can see that in the presence of CO2, now you have a catalytic process at the level of, I would say, iron 1, iron 0 porphyrin. Okay, and you can see that the current is important and it's almost a plateau here. Okay, and if you run a bulk electrolysis in this situation, you can show that the Faradic efficiency for the production of CO is close to 100%. So no hydrogen or little hydrogen is produced, mainly CO as a product, no other CO2 reduction product. And actually you can see on the reverse process here that you make CO because CO has a strong affinity with iron 2. And so when you go back here and you reoxidize your catalyst iron 1 into iron 2, this reoxidation is made easier in the presence of CO. This is why this reoxidation wave is shifted in the presence of CO, which is kind of an in situ proof that the product is CO. Okay, and so the process here is that you generate iron 1 here and then iron 0, and then you have a kind of a push-pull process where CO2 binds to iron 1, which is very nucleophilic. And then in the presence of acid, you will pull on the oxygen and get water out, and you make iron 2 CO, which at this potential is immediately reduced to release CO. Okay, from the plateau current, we can get the kinetic information. So an apparent rate constant for this overall process here. Okay, what is interesting is that if you change the concentration of a co-substrate, so as you can see, you need protons to release water, and the co-substrate here is a weak acid in DMF, phenol, for example. As you can see, as you increase the concentration of phenol, you increase the catalytic process and the plateau current. Okay, here you have to increase the scan rate to really reach the plateau, but it's possible. And so because as I've shown here, the plateau current depends on the apparent rate constant here, it's possible to extract from the change of the plateau current as function of the concentration of phenol. It's possible to extract the reaction order in phenol, and actually it's possible to show that at small concentration of phenol you have a reaction order of 2, and at high concentration of phenol you have a reaction order of 1, so that you can propose. And actually I should mention that we have shown that if you change the concentration of CO2, the plateau current shows a reaction order of 1 in CO2. So this means that the apparent rate constant is first order in CO2 and second or first order in phenol. So you can propose a mechanism where you first have addition of CO2 on the electro-generated iron 0 porphyrin, and then in the presence of of water or phenol you put on the oxygen to break the CO bond. So actually, this is the mechanism that you can propose, where you generate iron 0, then you add CO2. A first molecule of acid will stabilize the charge on the CO2, because actually you have a transfer of charge from the iron to the CO2 in this inner sphere process. And then with a second water molecule, you actually break the CO bond, and with this water, you get iron 2 CO, which is then reduced either at the electrode or by iron 0 to get iron 1 back, and with this CO, okay? And so here is the formal mechanism, where you have a catalyst, then a pre-equilibrium, then an irreversible process, and then a fast reduction. Okay, so in that situation, if the homogeneous reduction is fast, then the system is governed by 3 rate constant, so 2 dimensionless parameter, and it's possible to show that there is only one zone in the zone diagram. Of course, I don't have time to describe how we construct the zone diagram, but there is only one zone diagram that corresponds to the situation that you observe experimentally. And as I mentioned, here you can have 2 kinetic information actually. One from the plateau and one from the fact that, as you can see here, the half-wave potential is exactly equal to the standard potential, which means that the first irreversible chemical sequence is the rate determining sequence. And so what you get from the plateau is the overall constant for this pre-equilibrium times this irreversible rate constant, okay? And of course, the reason why you go from a reaction order of 2 in acid to a reaction order of 1 in acid as you increase the concentration of acid is because at high concentration of acid, you pull on this so fast that this process here becomes irreversible. And actually what you do is that you move this way in the zone diagram and you make this initial pre-equilibrium process irreversible. Okay, so this is what we can get from the experimental observation. Now that we have in mind the mechanism, the question is, what if we modify the porphyrin? And the way you can modify this porphyrin is to introduce substituent that will change the standard potential of the porphyrin. For example, if you put electron withdrawing group, you will of course stabilize the iron 0 by delocalizing the charge onto the porphyrin, and you will make the iron 0 porphyrin less reactive. And this is actually what you observe by putting those electron withdrawing group. You go in that direction, you get the standard potential more and more positive, okay? And as you can see, the catalytic current is decreasing. Of course, by increasing the scan rate, in each case, you can reach a plateau, measure the apparent rate constant. And interestingly, if you plot this apparent overall rate constant as function of the standard potential of the catalyst, you get a scaling relationship, which makes sense because if you stabilize iron 0, you make it less reactive toward CO2 and you decrease the apparent rate constant. Okay, so it seems that you are kind of stuck because what you would like is to get a high rate constant at positive potential, because as I said previously, the catalytic process is pinned at the standard potential of your molecular catalyst. Okay, so now the question is would it be possible to design a catalyst that will have a high rate constant but a positive standard potential? It seems from this correlation that if you use just electronic effect, it's not possible because of this scaling relationship. But we have shown that if you use through space effect, electrostatic through space effect, it's possible. The idea here is to introduce either a positive charge on the catalyst or negative charge of the catalyst, the idea is that with those positive or negative charge on the catalyst, you may stabilize or destabilize the intermediate in the process, because as I said previously, when CO2 binds to the iron, you sort of push electron to CO2 and you put those electrons on the oxygen. And so if you have positive charge here, you may stabilize this intermediate and so boost the catalysis. And this is exactly what is observed here. By putting those positive charge on the ortho position, we get not only a positive shift of the catalyst through electronic effect, but we have a stabilization of intermediate that makes the rate constant very, very high, and you get a very efficient catalyst. The same is observed if you put the positive charge on the para position, but it's less efficient. And if you put a negative charge, of course, you have the opposite effect, and so you decrease the efficiency of the catalyst. Okay, so this shows you that you can design better catalysts once you have understood the mechanism. Okay, so now let's continue on iron porphyrin, but with a different mechanism, with a different example, which is the production of hydrogen. So you can produce hydrogen by using iron porphyrins again, because once you generate iron 0, you can have a reaction here with an acid molecule to make an hydride, which can react with a second acid molecule to make hydrogen and regenerate the catalyst. So you have an EECC type mechanism. And what is interesting here is that, for example, if you look at what's going on using acetic acid as a substrate, okay, you can see that not only by increasing the concentration of acid, you get more and more current, but now you can see that there is also a shift of the wave. So it's not the same situation as the one we've seen previously with CO2, where the catalytic wave, the half wave potential was always at the standard potential. Now the catalytic wave is changing while the standard potential of the catalyst is still the same. So now you are in a situation where you have two kinetic information, one from the plateau, one from the position of the wave. And in the framework of an EECC mechanism, here are the analytical expression for the plateau current and half wave potential. And as I said previously, by combination of those two information, you can extract the rate constant. As you can see here, the plateau current is actually proportional to the square root of the concentration of acid, here protonated triethylamine, as expected here, whereas the half wave potential is independent on the concentration of acid, as you can see here, but it's not equal to the standard potential, okay? It's 100 millivolt more positive, okay? Which means that from this position here, you can get the ratio K1 over K2, and knowing the ratio K1 over K2, from the plateau current, you can get K1, and once you have K1, and the ratio K1 over K2, you get K2. So you can get a full characterization of the catalytic process. And interestingly, if you change the pKa of the substrate, the acid molecule, you get a correlation between the rate constant and the pKa of the acid, which is not surprising, because in each case, if you make the acid stronger, you get a faster formation of the hydride or a faster generation of hydrogen through a reaction of the acid molecule with the hydride. Interestingly, you can see that K2, so K2 is the formation of hydrogen, is slower than K1. So this means that in the process, you will accumulate hydride in the diffusion reaction layer. And this is an interesting situation. To finish on this reduction of acid using iron porphyrin, there is another interesting observation that we did observe that if you add a base in the medium, you get something which is very surprising, which is the increase of the catalytic process. as you can see here, as you increase the concentration of acid, you get more and more catalysis, which is kind of surprising because your substrate is an acid, you put a base and you get a more efficient process, okay? And so, as I mentioned previously, in those situations, you can measure the two rate constant, formation of the hydride and reactivity of the hydride, and both are changing as you change the concentration of the base. And then we did compare with the addition of a co-catalyst, which is not a base, but a phosphine, which is not a base, but can bind the iron in iron porphyrin. And what you observe is that with this co-catalyst, you get an increase of the catalytic current also, but no shift of the wave, which means that you only modify K2, the reactivity of the hydride. So here is the proposition to explain what's going on. For the formation of the hydride, the more important effect is actually the heteroconjugation of the acid with the added base, which increase the reactivity of the proton. Then, once you have formed the hydride, you get also an acceleration due to the more reactivity of the heteroconjugation between the acid and the base. But we have also observed that a non-basic species can also accelerate the rate. And the proposition is that if you have a ligand which is able to bind in a trans manner, probably on the iron hydride porphyrin, you will make this hydride more reactive and you will increase the reactivity. So this means that a co-catalyst can be just a ligand that will bind an intermediate in the mechanism. And because here, as I said previously, the second step of the process, so the reactivity of the hydride, is slower than the first one. You have accumulation of the hydride in the diffusion reaction layer. And so if you put a co-catalyst in the diffusion reaction layer, this will activate this intermediate and make the process faster. Okay, now that we know that iron porphyrin can reduce CO2 into CO, but can also reduce acid, which is a substrate, into hydrogen, we have a competition, okay, between making hydrogen and making CO in the presence of acid and CO2. But we can also maybe drive the reaction toward making formate, because, as I said, in the presence of a strong acid, you first make an hydride, for example, iron 2 hydride, and so you can say, okay, in the presence of CO2, maybe this hydride that accumulates in the diffusion reaction layer can react with CO2 or with the acid. And if it reacts with CO2, you might end up by making formate. And so you could change the selectivity. So here is the experimental example where you have iron porphyrin, an acid, okay? The reaction is very fast. You make hydrogen. As you can see, you have a sharp peak because you're in total catalysis. You consume all the acid during the CV. And now in the presence of CO2, you observe a second wave that corresponds to a reduction of CO2. And if you run the bulk electrolysis, indeed you observe hydrogen, but also formate. So here was the idea that I just mentioned previously. In this situation, you make iron 2 hydride that will accumulate in the diffusion reaction layer. And then this can react with acid to make hydrogen or CO2 to make formate. And because you have consumed all the acid by very efficiently at the beginning of the CV, then you just have iron 2 hydride that will react with CO2 or make formate. Is it possible? Actually, this is not what's going on. And it's possible to show that by just looking at the concentration profile at this position of the CV, for example. Because you have consumed all the acid in the diffusion reaction layer, as you can see from this total catalysis wave, This means that in the diffusion reaction layer, you don't have acid anymore. So here is the distance from the electrode, and you can see that there is no more acid. You just have hydride, okay? If you put CO2, CO2 will react with this hydride, okay? You will get formate and get back to iron 0, but there is no more acid to regenerate the hydride. So it's not possible to get catalysis here because you cannot turn over because of the absence of acid. Okay, so this means that the mechanism is different, and we have proposed a different mechanism that is also based on the observation of the role of a co-catalyst. Because if I go back to here, if you have consumed the acid, you have in the diffusion reaction layer a high concentration of the conjugated base of the acid, which here is a triethylamine because the acid was the protonated triethylamine. So now if you put the amine in the solution, you can see that actually you can boost the reduction of CO2, which means that this base, okay, this triethylamine or other amine or other tertiary amine can have a role in making the CO2 reduction more efficient. So again, we propose that what happens in the presence of a moderate acid is that actually you do not go through the formation of the hydride, but you bind CO2, okay, and then in the presence of an amine, for example, okay, you push more electron by binding the amine on, for example, the intermediate iron 2 CO2 minus, and so then you make the breaking of this metal carbon bond easier, and then in the presence of a weak acid, you will end up with formate. So this means that formation of formate does not necessarily go through the formation of an hydride, and this is what we have shown here, just based on the CV analysis and the observation of the product in bulk catalysis, and from the analysis of the CV, where we've shown that addition of base can boost the reduction of CO2 to make formate. So that what is important here, and the conclusion would be that when you have homogeneous catalysis, you can control the reactivity by changing, of course, the catalyst. I have shown that if you change the substitution of the catalyst, you can make the reaction faster or not. But you also have to worry about co-catalyst and co-substrate that can drive the reaction in different directions, and especially what matters is the spatial concentration profile that you have close to the electrode. So it's important to be able to understand that you have a two-dimensional reactor when you're doing homogeneous catalysis. And so then I will move to a different idea, which is, okay, now that we have investigated homogeneous catalysis, of course, if you want to move toward more efficient, not efficient, but practical system, you need to immobilize the catalyst onto the electrode. You cannot have catalyst flowing around in your solution. So then you move to supported molecular catalysis. And so very briefly, the idea is that if you have a film in which you put a molecular catalyst, now you will again have a diffusion reaction layer. But now the catalyst is not diffusing. What is moving are the electrons, okay, and the substrate into your film. And of course, the electron can move because you can have hopping between catalysts, but you can also, of course, put an electronic conductor in the film, and this is usually what people do, okay? So if you put a conductor into the film, now here is the situation. You have a conductor and you have attached your catalyst onto the surface of the conductor. And what is important is to realize that you have two different situations, as I mentioned previously. One is that if you have a linker which is large enough, this means that your molecular catalyst will be, let's say, away or in this outer Helmholtz plane of the double layer. So you will actually have a catalyst that will behave as if it were diffusing and pick up electron at the electrode, okay? Just that it's not diffusing, it's just picking electron in an outer sphere manner here, okay? So you have heterogeneous molecular catalysis. Now, if you have a different situation where the catalyst is adsorbed in some way onto the electrode, so that the electronic levels of your molecule will mix with the electronic states of the catalyst of the conductive part of the electrode. So, for example, carbon powder, carbon nanotube, or graphene, or whatever. And then this means that as you polarize the electrode, the electronic states of your catalyst will move with the Fermi level of your conductor. And so now you don't have a molecular catalyst anymore. And what has to cross the change of potential across the double layer is the substrate, and the current is controlled, I would say, by the fact that you have an ion which is crossing the double layer and no more the electron crossing the double layer as you would have here, okay? And I just want to mention here a paper that just came out in JACS a few days ago by Michael Mirking, showing exactly this effect, where you can have, even if you attach the catalyst in a way that its electronic states are not conjugated with the conductor, if the distance between the electrode surface and the catalyst is small enough, the molecular catalysis process will be driven also by the change of potential across the double layer, okay? So I would say that when you have a supported catalyst, okay, you really have to take care of whether you are in this situation or this one or in between, okay? And that would change the situation, because in this situation here, in absence of substrate, you do not see any current, because as you polarize the electrode, the electronic states of the catalyst are moving so that you do not trigger any electron transfer. You need the substrate to localize the electrons. And so I would like just to finish with that. In the case of CO2, there are some reports in the literature where, by using cobalt porphyrin as catalyst, okay, if you adsorb the porphyrin, cobalt porphyrin, onto the surface of the electrode, first of all, if you have a high concentration of catalyst, you have aggregation and it's not working very well. But if you use a low coverage, what is interesting, for example, here the support in that paper was nitrogen-doped graphene. It's possible to show that you have an increase of electronic density on cobalt atoms, which means, compared to the regular cobalt porphyrin, which means that you have actually a mixing of the electronic states of the cobalt in the porphyrin and the electronic states in the electrode. And so now, if you run catalysis, you have a very different situation from the one you had with the catalyst away from the electrode, because you cannot make the reduced form of the catalyst. You have a direct binding of the substrate onto the catalyst as you reduce the cobalt. And this is observed experimentally by the fact that now you observe an 120 millivolt slope, which is first order in CO2. So now your molecular catalyst behave exactly as a catalytic site as you would have with a metallic electrode. And so now you have a bridge between molecular catalysis and electrocatalysis. And so the analysis I showed previously for molecular catalysis is no longer valid in that case, and you have to work out the analysis in a different way. So now I will conclude that I tried to show you that molecular catalysis of electrochemical reaction correspond actually to an homogeneous reduction of the substrate in a thin layer close to the electrode. If you really have homogeneous catalysis, then you can control the amount of catalyst you generate by controlling the potential of the electrode, of course, and you can analyze the current in cyclic voltammetry to get kinetic information, okay? And then from this kinetic information, you can propose mechanism, and you can get more insight into the mechanism by changing either the substrate, the co-substrate, and the co-catalyst. And with all those information, you can design better molecular catalyst. Then the next step is transposition to supported catalysis. But as I try to show you at the end of this talk, it is kind of challenging. And I think this is the next direction the field should move on in the future. And with that, I would like to thank you for your very kind attention. And I'd be happy to answer questions. Thank you very much.
Thank you, Cyrille. It's a great talk. So let's see how many questions we have. Please go ahead and ask if you have any questions. Maybe I can start again. So you showed a couple of reactions. I'm curious about the nitrogen reduction reaction. Is it much more complicated? Of course, it should be to study, but are there any specific things that people should be aware of when it comes to molecular catalysis?
Of course, it's much more difficult in the sense that if you want to go all the way to nitrogen or to ammonia, starting from nitrogen, you have a 6 electron, 6 proton process, and so of course it's very difficult to get information on all those processes. And of course the CV, if you're lucky enough to be able to design a molecular catalyst that would be efficient, which is kind of challenging, the CV will not be able to give you all the information. But I guess that what is probably going on in such a situation is that you may maybe try to do the reaction step by step. So first reducing nitrogen to some kind of intermediate, and then try to further reduce this intermediate and go the step by step. And it's more or less the same situation with CO2. If you want to go all the way to, let's say, formaldehyde, okay, 4 electron, and then from formaldehyde to methanol or methane, you can maybe try to first reduce CO2 into CO, and then try to reduce CO, and so on and so on. But of course, as soon as you have more than 2 electron processes, it's very difficult to get detailed kinetic analysis. But at least you can try to get information on the rate determining step process.
Mm-hmm. Okay, thanks. We have a question from Linda.
Hi, yeah, thank you. Great talk. And also great transition, because I am actually currently working on exactly that, taking ambient dinitrogen to ammonia, and I confirm it is quite difficult. But one of the things that we are trying is this last point that you mentioned. So attaching known molecular catalyst onto electrodes. And one of the most open questions that we have that I would love your input on is the ideal tether length that we would need, the ideal distance that we need between our catalytic active site and our surface, depending on the kind of influence that we want from the double layer. And I would love any insight that you have.
So basically the size of the double layer is just few nanometers, right? So if the distance between the electrode or your linkage is like two carbons long a chain with two carbons, for example, then probably the molecular catalyst or the active site will be away from the double layer or in the outer Helmholtz plane, and you should probably not have any specific influence of the double layer. And in principle, if you're able to observe to analyze the CV of your electrode with the catalyst attached on it, okay, if you see the reduction of your catalyst, okay, you should observe a surface wave, okay, and by just changing the concentration of the supporting electrolyte, you should be able to see if there is any influence of the double layer, because by changing the concentration of the supporting electrolyte, you kind of change the size of the double layer. And so if your catalyst, if the redox center of your catalyst is not influenced by changing the concentration of the supporting electrolyte, this means that your catalyst will behave as a molecule in the system. Okay. If it's not the case, this means that probably your catalyst is actually adsorbed onto the surface in a way that the active site of the catalyst is kind of mixed with the electronic states of the electrode. I don't know if my answer is fine or not, but this is what I would suggest.
It's very
Of course,
helpful.
it will depend also on the kind of linkage you have, if it's conjugated or not. Okay, so of course, if you have a conjugation between your catalyst and the electrode, then you might have some kind of blurring between the electronic states of your catalyst and the electronic state of the electrode. And in that case, this means that you have not a well-defined standard potential for your catalyst. And so then you move away from molecular catalyst to something which is more like an electrocatalyst, in the sense that it is defined with metallic catalyst, for example, like gold or whatever.
One question that we have also from the chat that I'm just going in order. Haisu is asking about if it's possible to extract any quantitative information from the reverse scan of a CV curve.
Yes, it is. It is. For example, as I mentioned, in the case of CO2, because we produce CO, okay, you can observe the effect of CO on the reverse scan of the CV. If you have a catalytic process which is not very efficient, you may have also reoxidation of the catalyst, and so you can get information from the ratio between the anodic and cathodic current. Okay. Of course, you can also have information from the reverse scan if you observe new peaks, meaning that you have created new species. Again, also you can have information if you observe a crossing between the forward and reverse trace, which means usually that if you have a crossing, this means that you have created a species which is actually a better catalyst than your initial catalyst. Okay, and then by changing the scan rate, you can get more information. So of course, yes, in this lecture, I only discuss kind of ideal situation, and I showed you experimental results on systems that behave quite well, in the sense that there is no side phenomena. But of course, in many situations, you have side phenomena, which is like modification of the catalyst during the process, okay? And so if you accumulate in the diffusion reaction layer a species which is more active or less active, you will see it on the CV. Yes.
Okay, another good question that I'm also was hoping to ask is about the size of the molecule. So can we have, for example, if we have really like single ions, can we really do molecular catalysis? I'm presuming yes, but on the other side, if we have really large molecules that we use as a substrate, is there any like a limitation to which we can really treat it this way?
I would say, of course, I didn't mention that, but because I mostly consider the case where there is no limitation by diffusion of the substrate. But if there is some limitation by diffusion of the substrate, in the equations, the ratio of the diffusion coefficient of the catalyst over the diffusion coefficient of the substrate appears in the equation. I didn't show that, but so it's possible to take that into account. Of course, if for example, your catalyst is an enzyme, so a big molecule, of course, it will not diffuse. Okay, so then you will get in a situation where you will be closer to a situation where you have a monolayer of the catalyst. Okay, or if you have, of course, a substrate which is a very small molecule that diffuses very fast in the solution, you might be closer to the situation when there is no limitation by diffusion of the substrate, but you might have other limitation, which is, for example, the solubility, which is a problem, for example, if you try to reduce CO2 in water, because the solubility is small. So then you have to use tricks such as using a very thin layer or using a gas diffusion layer. And of course, there are limitations in that sense. So I think that if you use regular molecular catalyst, like even porphyrin, which are big molecules, but it's fine. I mean, the diffusion coefficient is not that small, and so the analysis is still valid, of course.
But if you use something like an ionic liquid as a medium, then things become much more complicated.
Then of course you have to worry about the diffusion coefficient, but then of course it will depend on the scan rate you are using and so on. So
Cyrille, I also have a question also about one thing that you mentioned in the beginning. I didn't ask at that time. So you mentioned durability. The question that I have is, I mean, when it comes to the surface, we know that the surface can be damaged in electrochemical experiments. And the way that it gets damaged is more or less clear, at least generally speaking. But if we speak about the molecular homogeneous catalysis of the molecules, what is the durability in terms of the number of turnover numbers? Because if I can imagine a molecule going through redox cycles, why would it just get destroyed at some point? Going through the same redox cycles, what would be the actual trigger?
So you might have different dead end pathway, I would say. So one is that your ligand might not be strong enough, in a sense that, of course, you can have some chemistry on the ligand. Let me take an example. If you use, for example, iron porphyrins, okay, the example I gave, in absence of co-substrate, which is necessary for the reaction to be fast enough because you need to put out the oxygen. Because there is some delocalization of the electronic density on the ring, okay, you may have carboxylation of the ring because CO2 may add on the porphyrin. And of course, you have degradation. Similar, in the same way, you can have protonation of the ligand, okay? And so if you have protonation of the ligand, in many cases, you may have decoordination of the metal, and then because you are at a negative potential, you have a free cation, and you will make deposition of a metallic species on the electrode. Sometimes it's good. There are some examples where actually you use the molecular catalyst as a pre-catalyst because you destroy the molecule and you deposit something onto the electrode, which is actually a good catalyst, but sometimes it's not. So the transformation you can have are due to the fact that actually you cycle your catalyst at with different redox state, but there is delocalization, of course, of electrons onto the catalyst, the ligand, and this can trigger some chemistry on the ligand.
Okay? So would it be better to say that it's better to fundamentally at least view the lifetime of the activated molecule rather than the turnover number before it gets destroyed? Yes.
So this is why I think this is what I tried to show, but it was quite quick. Here, if you, here, if you calculate, if you determine the maximal turnover number, okay, for a very simple system like this, you can see that this value depends on the lifetime of the catalyst. Okay, if you have a decomposition process of the catalyst. And it's the same if you do photocatalysis, for example, you have exactly the same problems.
But as a quantity that should be reported, it's better to report the turnover number or the lifetime?
I would say that probably the turnover number is better for given for a given situation, for given conditions, because as you can see here, the maximal turnover number will depend on the lifetime of the catalyst in the given conditions, divided over the rate constant, which also depends on the conditions, if you have a co-substrates and so on. Okay.
Okay. I also saw somebody turning on the microphone. So if someone wants to ask directly a question, please go ahead.
Yes, I had a question that is more or less connected to what you said earlier regarding the size of the molecules. So you said regarding the calculation of the turnover frequency that you gave earlier, that you needed to take into account the amount of catalyst that is in the diffusion layer, right? But there are a lot of papers where actually what's taken into account is the amount of catalyst only at the surface of the electrode. And I was wondering, why is there a difference?
So if you have a catalyst which is immobilized onto the electrode, it's correct to use the amount of catalyst which is onto the surface, okay? Because then there is no diffusion of the catalyst. If your catalyst is free to diffuse, okay, then you need to use the amount of catalyst which is in the space where the reaction takes place. And this space is the diffusion reaction layer. And actually, this diffusion reaction layer, you can see it as if you had a two-dimensional film of active form of the catalyst. The point is that this catalytic film, I would say, its size depends on the efficiency of the reaction. But actually, if you think about it, if you use a thick film with immobilized catalyst, it's the same, because the amount of catalyst that will be active depends on which on the catalyst you will be able to address or to activate. And if the electron transport is not efficient enough, you will also have a diffusion reaction layer within your thick film. And so this is something that has been studied and observed in many systems where you have immobilization of the catalyst in a polymer, for example, if at some point you increase the size of your polymer, thinking that you will have more and more catalysts, so more and more current, actually you observe that at some point it levels off because you're not able to activate all the catalysts, because those which are away from your underlying electrode surface are not able to be activated by the electrons, I would say. Okay, so you also have a diffusion reaction layer if you have a thick film of catalyst. Very similar, but what is diffusing in that case, it's not the catalyst, it's the electron or the substrate. So this has been described, okay? And so this means that if you want to get the true intrinsic activity of your catalyst, you have to know how many molecules you're able to activate, because you have to report the amount of product you make to the amount of molecule that you have actually activated. Okay.
Yeah, thank you very much. I just wanted to have a precision regarding, you spoke earlier about the crossing that you sometimes observe. So not perhaps to do a full expose on why this happens sometimes, but this is a little shady to me, and you gave some explanations. So 10 minutes ago.
One possibility is that if, let's say you have a process where you generate your catalyst, it reacts, and you make an intermediate, okay, and maybe this intermediate might be transformed into a species which is actually more active, which means that as the reaction is going on, you are producing a better catalyst in the diffusion reaction layer. And so on the way back, okay, this, of course, because you produce this catalyst through a chemical reaction, okay, you will have a concentration of this new catalyst, I would say, which depends on the position from the electrode. And of course, away from the electrode, you will produce more of this new catalyst because you give time to the transformation to take place as your initial catalyst is diffusing, the active form is diffusing away. And so now your new catalyst will diffuse back to the electrode to get active. And this is why you see its better activity on the way back. Okay, so now on the way back, you have a new species which is diffusing back to the electrode and being active. And so you observe more current. This is the reason why you observe a crossing. I'm not sure if it's clear, but
yeah,
this is the idea. Okay,
thanks.
Okay, maybe we can finish with the last question that Lindy is asking in the chat, because we're always getting back to the heterogeneous catalysis, even though we're mostly discussing homogeneous one. But I should say also that we will have the discussion of the double layer and everything connected with heterogeneous reactions later in later colloquiums also. So just please stay tuned if you're interested in this. But the question is about the effect of the electric constant estimation from, say, CV or any electrochemical measurement.
So you mean to get an evaluation of the dielectric constant within the double layer? Maybe it's possible. I'm not very familiar with that, but I'm not sure.
I mean, I guess you can do through the impedance.
Yeah,
this
maybe.
estimated.
Yeah, maybe. Yeah, that has probably been done, but I'm not very familiar with that. So probably the impedance is the best way to do it. Yeah, sure.
Okay, so maybe then we can wrap it up if we don't have any more
Sure.
questions. So thank you so much, Cyrille. It was really nice
you very much.
to learn about the molecular catalysis. And it's nice that we have such an engaging audience this time. So I hope that we will keep it. And so I hope to see everyone again next time. So next time we'll host Francis Ross from the MIT, who will be talking about the use of the transmission electron microscopy and liquid cells and how to bridge it to electrochemistry. So this is sort of an emerging field that is emerging because of the new technologies that we have. And so hopefully we'll hear a lot about it. So please stay tuned. Thank you so much.
Thank you very much.
Thank you.
Bye-bye.